Last time I finished building the transformer class, combining the encoder and decoder, and then uh, calculate predictions using that. This time I fixed the masking and cross attention issues and started data pre-processing. So let's start with the masking and cross attention. This line creates a look ahead mask, um, which I made as a part of the decoder class. And then here the decoders pass the encoder output and the look ahead mask. So let's take a look at those. This function creates the mask, and basically the reason the masking is important is because the decoder shouldn't know data from the future, because obviously while it's trying to predict, it won't know data from the future. And what that looks like is a upper triangular matrix of negative infinity, which is added to the attention matrix. And then once it passes through softmax, then all those values go to 0. So the decoder won't have those values. Okay, in the call function, the the transformer block is past the the mask and the encoder output. So let's go to that. Um, yeah. So the mask is then passed to self attention, or it's added to the other self attention matrices, and then if the encoder output is provided, then it calculates the cross attention score. Then it adds it to the self attention score, and it's normalized and passed through a feed-forward network. Um, no, it's past the feed-forward network, then normalized. Sorry. Um, yeah, that's basically it for the model. For the data pre-processing, I first of all I'm using. Let's see, where's my data set? I'm using this Microsoft data. It's taking the values from 2024 to May 5th, 2025. And it has the closing price, the high price, low price, the open, and the volume. But right now I'm only using closing price. So this creates time series data. We're using a sliding window. So basically my input window is 60 and my target time frame is 20. It uses 60 values from the input and uses the last value of that to predict the 20 values of the next 20 percentage changes. And basically a sliding window is better than going time frame to time frame or time step to time step, because it can capture larger patterns. And this splits the training features and the target feature into training and validation data using a rolling window. So it splits the data into n splits amounts. So I have 3 sets of training and validation data. This one prepares the data model. Um, it initializes the prices, data frame, and it fills in the missing values using interpolation. And then this is just a check if the the data set is large enough. Um, and this creates the data. This splits the data into training and validation. This creates a transformer, and it returns the model and the splits. These are callbacks, which is basically um, functions or things that run while the model is running. So this is early stopping. It helps prevent overfitting. This reduces the learning rate as time goes on, or if the loss is plateauing, and this is to save the model parameters in certain points. This function trains the model. Um, First, it compiles the model using optimizer. This uses Atom, And then I use the mean square error loss function, and what this means basically is this is the how the model is going to be evaluated and how it learns. It uses this and tries to minimize it using gradient descent and backpropagation. And these are the metrics that I use to see how the model is performing: mean absolute error and mean square error. And then it creates the callbacks, and then it the model trains it for the number of training and validation sets I have. So it trains it 3 separate times, with 3 times with different data, and this fits the data. And then this this basically for plotting, like, so we can see what the learning is like, or how the loss function is over training. Um, this one, this function evaluates the model using the metrics. It basically prints out um, all the metrics in splits. And this is just for plotting. And then here, we also combine all of that. So let's talk about some problems with the data. Or let's talk about some problems with the model. Not this. So this model will function if this line is run, which is configures TensorFlow to run functions eagerly. And what that means is usually TensorFlow uses a graph, which is its interpretation, its model of how the model functions. So what TensorFlow does, it passes through all of this using like empty tensors, and then the problem I've been getting is with this line. Basically, it says as list is not defined for a symbolic tensor. What it means is like those empty tensors don't have a as list representation, so the model kind of breaks. But with this line, the model runs, and it has an average loss of 16.70, and an average compile metrics of 3.24. So in the next video, I'll try to fix this error, because TensorFlow graph is usually more efficient, so we don't want to use this line. And then I'll also try to experiment with hyperparameter tuning. And yeah, that's about it. Thanks for watching.